In this video, we're going to talk about how log transformations can be used to convert some nonlinear relationships into ones that are linear in the transformed variables. Before we talk about the use of logs, though, there's just a few properties we should review. You may have seen this in a high school algebra class or some other class, but it's probably helpful to review some of these concepts now. We say the log base a of x equals b if a to the bth power is equal to x. In other words, the log function tells you the exponent that you have to raise the base of that logarithm to in order to get the value of x. There's a few basic properties that we should just discuss now. One is that the log of a product is equal to the sum of the logs. So the log of x times y is equal to the log of x plus the log of y. The log of x to the 8th power is equal to 8 times the log of x, which is essentially just an extension of the previous property because you're multiplying x by itself 8 times. The most common log, and the one that we'll be using in econometrics, is the natural log, which is a log base e. We're not going to talk about this in detail, but we can just note that e is approximately equal to 2.71828818, and that continues on indefinitely. We're going to use these properties to talk about some applications in which the log function is going to be helpful in econometrics. Suppose we take this function where we have y is equal to the product of beta 0 times x1 to the beta 1 power, x2 to the beta 2 power, and so forth, out through xk to the beta k times e to the u power. We can simplify this using those properties of logarithms. When we take the natural log of y, that's going to be equal to the log of the product on the right-hand side. And the log of the first term is just the log of beta 0, and we add to that the log of the term x1i to the beta 1, but we know that that's equal to beta 1 times the natural log of x, and so forth all the way through this equation. So what we've done here is we've taken a relationship which is multiplicative and converted it into one which is linear in the logs of the dependent variable and all of the independent variables. This is one of the applications where the log transformation is going to be useful in econometrics. Another way of expressing that is just to define new variables, y tilde, x tilde 1, x tilde 2, out through x tilde k, as well as a new constant term, beta 0 tilde. In order to use this transformation, if you have data on the variables y, x1, x2 through xk, all you need to do to estimate that model in a multiple regression framework is to take the log of the dependent variable, the logs of each of the independent variables, and just run a regression of the log of the dependent variable on the natural logs of each of the independent variables, and we get estimates of the slope coefficients beta 1 through beta k, which are the exponents in the original equation. We're not going to go through a derivation of this here, but when we have this relationship that's linear in the logs, each one of those slope coefficients, beta 1 through beta k, turns out not to be a measure of the slope of a relationship between y and each of those x variables. Instead, they represent elasticities. And as you may recall from an introductory microeconomics class, the elasticity of y with respect to x is nothing more than the percent change in y divided by the percent change in x. So when you estimate this equation, you're estimating not the change in the level of y that occurs when one of the x variables changes by 1 unit. Instead, you're measuring the percent change in y that occurs when x changes by 1%. For example, if we were to estimate a demand function where the log of the quantity of good x demanded is equal to a constant times the natural log of the price of good x plus another constant times the natural log of the price of good y, plus other variables out through beta k times the natural log of income, beta 1 is going to be equal to the price elasticity of demand for the good. So that's where we get the estimates of the price elasticity of demand that you may have seen in introductory microeconomics or intermediate microeconomics classes or other applied microeconomics courses. The coefficient beta 2 is a measure of the cross-price elasticity between goods X and Y. It tells you what percent change in quantity of good X will occur when you change the price of good Y by 1%. And thinking back to your principles of microeconomics, if that's positive, it tells you goods X and Y are substitutes. If it's negative, it tells you that they are complements. The coefficient beta K is a measure of the income elasticity of demand. It tells you the percent change in the quantity demanded that occurs when you change income by 1%. If that's positive, we know the good is a normal good. If it's negative, it tells us the good is an inferior good. If it's greater than 1, we know that the good is a luxury good. If it's less than 1, we know the good is a necessity. When people estimate equations such as this, that's the source of all those estimated elasticities you've seen in prior economics courses. If we plot the relationship between quantity and price without taking logs, we'd see this nonlinear relationship on the left, in which the price elasticity of demand is constant, where the ratio of the percent change in quantity demanded to the percent change in price is the same everywhere along the curve. But if we were to plot the log of quantity and the log of price on the same set of axes, we'd end up with a linear relationship in the logs of these variables. And if you're dealing with a bivariate relationship, simply plotting out the relationships between the two variables and the logs of the two variables can give you some idea of whether the relationship is linear or perhaps it's linear in the logs of the two variables. And in this case, as noted on the screen, this would occur if beta 0 is greater than 0 and if beta 1 is negative, which would be what we'd expect in the case of a demand curve. One example where this is used quite a bit in econometrics is when we're working with a function called a Cobb-Douglas production function. And in that function, the quantity of output is equal to a constant times one input, in this case labor, raised to the power beta 1, times capital, which we normally denote by the letter K, because C is used for so many other things, raised to the power beta 2. This is clearly not a linear relationship, but when we take the log of this function, we get the log of quantity is equal to the log of beta 0 plus beta 1 times a log of labor used plus beta 2 times the log of capital. One of the things we often do is we want to test whether we have constant increasing or decreasing returns. And one of the things which is discussed in the textbook is that we have constant returns to scale if the sum of beta 1 and beta 2 equals 1. We have increasing returns to scale if the sum is greater than 1. And we have decreasing returns to scale if the sum of those coefficients is less than 1. As you might guess, this is a case where we can use a wall test to test for the linear restriction imposed by constant returns to scale. And if we cannot reject the null hypothesis that beta 1 plus beta 2 equals 1, that would suggest that we can't reject the possibility of constant returns to scale. So this is just one example of how we use log functions in econometrics, and we'll see many examples of this throughout the rest of the course. And we're also going to look at, in the next video, what happens when the log of a variable appears only on the dependent variable or only on the independent variable.